Today I'm going to show you the different aspects of an IPv6 addressing protocol and a few different IPsec protocol implementations. First, we will delve into the bare-bone foundation that helps create proper IPv6 addresses. IPv6 addresses are valued at 128 bits total versus IPv4's 32-bit total. I've started off by creating a random IPv6 address, and I will go about breaking it down into sections that can make the process of understanding IPv6 much easier. IPv6 addresses have 8 octets, or hextets. Each octet has a base value of 16 bits. Each number or letter grouped together by 4 are valued at 4 bits each. So this 9082 octet, the 9 is worth 4, the 0 is worth 4, and so on, equaling 16 bits altogether. Being that there are 8 groups or letters or numbers that create IPv6 addresses, we can multiply each octet by the base value of each group for a combined value of 128 bits. 8 times 16. Next, we're going to delve into the binary notation portion of the IPv6 address. You can see here using the A421 method, and keep in mind that the hexadecimal base value is 16, that the 9 of the first octet, of course, is the 8 and the 1 turned on, the 0 all off, the 8 portion turned on, and the portion on the far right, the 2, is the second to the most right. Now, we're also going to mention the hexanumeral values of A and F, A being 10 and F being 15. You can see down here I have created a little chart, 10A, 15F. Now, it's the same thing using A421. You can easily combine the numbers to get your base value of 10 through 15. Makes it much easier to understand IPv6 addressing. Alright. However, if you take a look at the hexadecimal chart, you can see that it may be similar to the base 10 decimal value. The base 10 decimal value being 0, 1, 2, 3, 4, all the way to 9. Counting the 0 is a base value of 10. Makes it much easier to understand if you already know base 10. You just count up from 9 to 15 using A, B, C, D, E, F in a return of the numbers. Excuse me. You can pair these to each hexanumeral value that's associated with each IPv6 addressing portion. There's also other techniques to make IPv6 addressing much shorter. For instance, the multiple zeros, leading zeros, and implementing the double colon. Multiple zeros is basically taking any zeros that are next to each other on the farthest left portion of the octet and removing 1. So if there were 3 zeros in this octet in particular, let's say it was 00F, you would get rid of the 2 zeros and leave the 1. So it'd be 0F instead of 0AF. Also, if you were removing leading zeros, you remove the leading zeros from the farthest left portion of each octet. So for the 0321, remove the 0, the 2 zeros for the second octet removed, and the 2 zeros on the 8th octet removed. However, you do not mess with the zeros that are not on the leading left portion. Those are not to be messed with. Also, this works the same with multiple zeros. You don't remove the zeros in the middle. They have to be on the left portion of the octet, the leading portion. And also, the implementing the double colon. Right here you can see that I changed this IP address, and the first 4 octets, a string of zeros, can be easily removed, and the new IP address can come out as 9082 double colon 1234 all the way to 0100. Now, being that there are 4 octets that are readable, you can see that the middle portion between, or the double colon between the 9082 and the 1234 must have 4 leading zeros, or 4 strings of octets between the 9082 and the 1234 octet. Devices will add portions of the address that have been shortened. So any techniques that use to shorten the address will be, or the devices will make up for it, and the address will be written out properly. Next, I will be discussing the implementation of IPsec in the main IPv6 header, protocols that work alongside IPsec, and its values towards security for the networks. Now I will discuss the implementation of IPsec towards the security of a network and the variety of its protocols. IPsec can be used in either an IPv4 setting or an IPv6 setting. However, this information will be catered towards IPv6. 2 protocols in particular I would like to analyze that are involved with ensuring packet authentication and integrity are the authentication header and the encapsulating security payload. The standards were established to help protect vital information that is transferred over the internet. The authentication header, like its name suggests, authenticates packet information so that the source and the destination nodes that are sending information are the correct addresses that are supposed to receive such information, and that the information being sent is not altered in between source and destination, also known as integrity. ESP, on the other hand, provides encryption as well as authentication and data integrity. Encryption is applied towards information by altering its language with what is called a cipher or algorithm, making the information altered by the cipher unreadable until it reaches its proper destination, which by then has become legible by users who possess proper access to such information. Next, I will discuss IPsec tunnel mode. Tunnel mode, used commonly between 2 routers or a VPN client and router, encrypts IP packet traffic so information transported from one local network to another separate local network will have a higher standard of security. This means that IPsec wraps the original IP main header, encrypts it, adds a new IP header, and sends it to the other side of the tunnel to either said VPN client or gateway. Now you can see here in diagram 1 that PC1 wants to send PC2 an IP packet by using IPsec tunnel implementation. The process is somewhat straightforward. PC1 sends the IP packet to their gateway to leave their local area network. The gateway, configured with IPsec tunnel mode, encrypts the IP packet, and for argument's sake, let's say that we are using ESP as our IPsec configuration. The IPsec ESP header will be inserted between the main IPv6 header and the upper layer protocol. From there, the packet is sent along the tunnel's interface, passing from one neighbor router to another, before reaching its final destination gateway. Keep in mind that IPsec tunnel implementation doesn't allow neighboring routers to intercept packets sent along a tunnel interface. They simply act as the packet's pathway. After the packet reaches its destination gateway, the packet will be decrypted and sent through the destination LAN, which in this case will be LAN 2, ultimately reaching its correctly established client, PC2. And last but not least, the foundation that makes up ESP and AH packets. IPv6 as a whole can be quite difficult to grasp in just one video. However, I hope that the knowledge I have set forth for you, being IPv6 addressing, or IPsec, can continue to prove useful to you in many tech-related situations to come.